Hi, everybody. I'm Donald Boyce. For my role in this work, actually, I did this under contract with Air Force Research Laboratory. Um, it's going to be a kind of a different talk because you're not going to see any equations and you're not going to see any plots of anything. It's really going to talk about how we want to use what we want to do with FEniCSx, what we're doing, what we want to do, and how we want to do it. The way it's going to go, I've sort of developed a framework for using FEniCSx as like the finite element engine in the material modeling. And so I have like basically 4 slides to talk about that and just give the big picture and sort of present it maybe as, a useful idea beyond just our group. Maybe it's applicable to other people, but even if it doesn't exactly work for you, you might still find some interesting ideas, in the and things in there. So after those 4 slides, I have like 5 slides that go through what actually the inputs look like and how to run a job. In fact, so if I'll probably be rushing through that. So the 2 takeaways for that is there's a job class where you can create a job from like a handful of named inputs, and then the second thing is actually how to run. There's a mechanism for running jobs in batch, running a sequence of jobs. So for that, you create an iterator, and the iterator is not exactly on the jobs, but what it is, it's on keys that you can use to generate the jobs. So effectively, it's that. So that's the idea of the batch, is just have an iterator and just run jobs one after another. Okay, so let's get to it. So the first slide. So I didn't really want to actually talk about the actual polycrystal modeling because that's not really the focus. It's really the focus is really going to be how we're using the finite elements in this process. But on the other hand, it would be kind of it needs some context. It wouldn't really make any sense if I just started going into the code without actually any background on what we do. So here I'll give this one slide, sort of quick rundown of sort of what the modeling program is. So like the summary version of this slide is here we are, we're a group. We have certain materials that we're interested in modeling. Not everything, just there's certain materials of interest or a class of materials of interest. We can get experimental data. We do experiments and generate empirical data. We're not the only ones who do it. There's other people doing the same thing, and they could also use to benefit from our code. And then finally, we get down to sort of what we want to do with our material modeling. And there's a number of things, but we're not trying to solve every PDE in the world. We just have a handful of ones that we want to solve. So that's kind of the overview, but to get a little more specific about what we actually do, what is polycrystal modeling. The thing to understand to get you started would be like the orientation field that we need. Okay, and to explain that, we'll start with sort of a single crystal, which has a regular lattice, over some region of space. And now if you take that, you can see there's certain rotations where you could rotate it, and it's going to look exactly the same. And those are the crystal symmetries. So there's a crystal symmetry group associated with that. On the other hand, if you just sort of leave it fixed and you sort of look along different directions and just sort of look at the way the atoms are spaced, certain directions will be close packed, other ones will be different. So that means that it's going to respond differently in different directions. So there's an inherent anisotropy there. Next, nevertheless, there are certain recognizable crystallographic directions. And in fact, you can set up an orthonormal basis based on the crystallographic directions, the way the crystal is oriented in space. Okay, and so now, if you want to go look up, say, the the anisotropic moduli for copper or titanium or something, the values you get are always relative to the crystallographic reference frame. So that means if you actually want to, solve a problem, you need more than just the moduli. You need to know how the crystal is oriented relative to the frame that you're working in. So that's the idea of the crystal orientation. Effectively, the way we use that is there's basically an orientation field, and each crystal has an orientation matrix which converts back and forth between the crystallographic reference frame and the sample frame. So pretty much that's the idea. Now then, so that's the single crystal, and then polycrystal is what you get when you put them all together. So you pack them all together like fans at a Taylor Swift concert, and you get sort of the picture on the bottom. And what that's just showing, this is actually a real material, a nickel alloy. That's about really 1 millimeter section across. And it's just colored just by grain ID. So that's what the crystals look like. Each one is like a separate crystal, and they're all packed in together. So pretty much that's what we're modeling. But really a lot of the question that we're looking at is the effect of the orientation field, on the properties as we deform it. And so our experiments, we use high energy X-ray diffraction. So I mean, the one question is how do you measure the field? How do you look at a specimen and actually get the orientation field? And sparing you the details, shining high energy X-rays, we can get that information. In fact, actually get a detailed map, even more, including strain, and like centroid and location and things like that. So pretty much that's what we're interested in, and probably the biggest focus is really the effect of the orientation field on the results. Okay, so then that leads sort of the considerations and goals. And, so first of all, I hate to break the bad news to you, but not everybody understands, functional analysis, the functional analytic framework of, I'm crying too, So in fact, actually, it's a non-trivial thing to learn. You can't expect everybody to know that. And actually, a lot of the people, so beyond my particular research group that I'm working in, if we wanted to share this with other people, we can't really expect them to know all that, right? And not only that, there's other considerations. Not all users, research scientists are not software developers, right? So there's, if you work with people, there's a pretty wide range of their capabilities. I mean, some are very good and some are, pretty basic. So here are the things. So by the way, there's some work, in learning Phoenix or FEniCSx in this case. And I'm not complaining at all, because there's sort of a different scope. Here I have a handful of problems I want to solve. I'm not trying to solve every, every PDE. So I'm not complaining about, the API for Phoenix. I just want to simplify it for other users, And then so that process is going to involve basically hiding the technical programming, technical details, both programming and mathematical, and then so that it's easier for people to use. But also, I do want to provide interface for scripting sequences of batch jobs, because nobody ever runs just one finite element simulation, right? How many times have you heard, I'm done the simulation, let's write the paper now, So now the other thing, since we're planning to use multiple material processes, like thermal, analysis, as well as, elasticity and slip, putting them all together lets you sort of reuse some components. And then finally, the other thing I want to do is separate the material modeling from the finite element execution or the implementation of the finite element. Yeah, so but in the process, when you do the material modeling, pay attention to the details so that it can be used efficiently in the finite elements. It's not part of the finite elements, but okay, so 2 out of 4 down. Now here's a really simple, this is a really simplistic thing. When I first saw Phoenix, it just sort of, this was my motivation. It's kind of a, just sort of walking through there's a certain kind of UML diagram. I forget what the name is, but it's like a phone chart. Oh, I'm sorry. Oh, okay. 2. Okay. But at any rate, so this 4 groups of inputs: mesh material, polycrystal configuration. That's the grains. So let me get to this. This is really the key point, really. So here's what the design of our system is. Okay, the blue ones are the polycrstalx packages, and the orange ones are the main package. And here, polycrystal, you don't see the details because it's about finite element implementation. And plus, okay, well, I'll move on. Finally, okay, so from the user side, the user just sees the inputs module and the polycrystal module. The inputs module is really a passive module, just gives containers for the user to deliver the data for the function. So if you're doing elasticity, deliver a force density function, a list of boundary conditions for tractions, a list of boundary conditions for displacement. And that's all it does. Okay, and then here's the actual finite element implementation. When the user, okay, so the gray boxes are actually the user, or actual data for the problem. It takes the input specs. Okay, the process, it knows which process is running. It creates a blank form. Everything is 0. And then it uses the loaders to process the input specs and fills in the form coefficients. And voila, you're done. Okay, so my time is probably up. So here's just sort of a quick walkthrough as expected. So the job, you get a job like this. Turns out material is actually pretty easy. Okay, there's mesh input. Yeah, the interesting thing is there's boundary sections that are all done by name. You can name boundary sections and then specify boundary conditions by that. And then finally, the batch. And finally, how bad was I?